In this video, we will discuss the meaning of the concepts and formulas that we've been using in the previous videos in this series. If you're not interested in or don't have the time for a discussion of these topics, then you can simply proceed to the next video in this series, which contains another Newton's second law problem. To begin, let's discuss the difference between the force of friction and the coefficient of friction. Loosely speaking, the coefficient of friction measures the roughness of the surface and the object. For example, ice would tend to have a small coefficient of friction because ice is smooth. Sandpaper would tend to have a large coefficient of friction because sandpaper is rough. The coefficient of friction takes values between 0 and 1. Don't confuse the coefficient of friction with the force of friction. The magnitude of the normal force exerted by the surface on the object measures how firmly the surface is pressing against the object. So the meaning of this formula is that there are two factors that affect the magnitude of the force of friction. The rougher the surface or the object, the greater the force of friction. And the more firmly the surface is pressing against the object, the greater the force of friction. I think that both of those factors will match your common sense understanding of how friction works in real life. Now let's review the difference between velocity and acceleration, which we already began discussing in the previous videos. The direction of the velocity vector indicates the object's direction of motion. In video 1, the block was moving to the right, so the velocity vector pointed to the right. In video 2, the mass was moving parallel to and down the hill, so the velocity vector pointed parallel to and down the hill. And in video 3, the box was moving to the right, so the velocity vector pointed to the right. The direction of the acceleration vector does not indicate the object's direction of motion. So, what does the acceleration indicate? In physics, the term acceleration refers to speeding up, or to slowing down, or to changing the object's direction of motion. So notice that the term acceleration has a broader meaning in physics than it does in ordinary language. Here are some rules that we can use to help us interpret the acceleration vector. In video 1, the block's acceleration vector is parallel to the velocity vector, so the block is speeding up. In video 2, the mass's acceleration is parallel to the velocity, so the mass is speeding up. In video 3, the box's acceleration was anti-parallel to the velocity, so the box was slowing down. In video 3, the acceleration points to the left, but the box is moving to the right. That confirms that the direction of the acceleration vector does not indicate the object's direction of motion. I've mentioned that in general, the direction of the acceleration vector does not indicate the object's direction of motion, but now I have to mention an important exception to that pattern. If the object starts from rest, then the direction of the acceleration vector will indicate what direction the object will begin moving. And many physics problems do involve objects that start from rest. So for those problems, the direction of the acceleration vector will indicate what direction the object will begin moving. Acceleration is a difficult and subtle concept. I think that historically, the lack of a clear concept of acceleration and the failure to carefully distinguish between the concept of velocity and the concept of acceleration was one of the most significant barriers to the development of the science of physics. So remember, don't confuse velocity with acceleration. Now let's discuss Newton's first law. Newton's first law says that if the net force on an object is 0, then an object at rest will remain at rest. And if the net force on an object is 0, then a moving object will continue to move in a straight line with constant speed. The surprising part of Newton's first law is that if the net force on an object is 0, then a moving object will continue to move in a straight line with constant speed. Imagine a puck sliding along a very smooth surface, such as very smooth ice or a giant air hockey table. In fact, let's imagine that the surface is perfectly smooth. Again, imagine that the puck is sliding along this very smooth surface. According to Newton's first law, if you don't touch the puck, then the puck will continue to slide in a straight line at constant speed indefinitely. Now, actually, any real-world surface is at least a little bit bumpy. So, in the real world, even on a very smooth surface, the puck will slow down very gradually. Even on very smooth ice, the microscopic bumps on the surface provide tiny taps that very gradually slow the puck down. But if we imagine an ideal surface that is perfectly smooth, then once the puck is moving, then the puck really would continue to slide in a straight line with constant speed indefinitely. In outer space, where there is almost zero friction, a moving object will indeed continue to move in a straight line at constant speed indefinitely. According to Newton's first law, once an object begins moving, no force is required to explain why the object continues to move. Have you seen the movie WALL-E? In that movie, there's a scene where the robot, WALL-E, is floating in outer space. WALL-E is holding a fire extinguisher, which he can use to provide a force on himself. Once WALL-E is moving, if he doesn't use the fire extinguisher anymore, then he will continue to move in a straight line with constant speed indefinitely. Once WALL-E is moving, no force is required to explain why he continues to move. In video 3, the box was already moving to the right when the problem began. Therefore, no rightward force was required to explain why the box continued to move to the right during the problem. Now, in video 3, the box experienced a leftward force from friction. So instead of continuing to move to the right indefinitely at constant speed, the box slowed down and eventually came to a stop. The kinetic friction provided the net force, which slowed the box down. We've seen that, according to Newton's first law, once an object is moving, no net force is required to explain why the object continues to move. But what about if the object begins at rest? Well, according to Newton's first law, if an object begins moving from rest, then a net force is required to explain why the object began to move. Now, many physics problems do involve an object that begins moving from rest. So for those problems, remember that if an object begins moving from rest, then a net force is required to explain why that object began to move. Now, let's discuss the meaning of Newton's second law. To review, the direction of the velocity vector indicates the object's direction of motion. The direction of the acceleration vector doesn't indicate the object's direction of motion. Instead, acceleration refers to speeding up or slowing down or changing the direction of motion. This expression stands for the net force in the x component, and this expression stands for the net force in the y component. The sigma symbol means add, so these expressions remind us that the net force is the sum of the individual forces. These equations represent Newton's second law. According to Newton's second law, the net force at a particular point in time determines the acceleration at that point in time. The net force at a particular point in time does not determine the velocity at that point in time. So, the meaning of Newton's second law is the net force at a particular point in time does not determine the object's direction of motion at that point in time. Instead, the net force at a particular point in time determines whether the object will be speeding up, or slowing down, or changing its direction of motion at that point in time. For example, in video 3, the net force was to the left. This did not mean that the box was moving to the left. In fact, we know that the box was moving to the right, even though there were no forces to the right. Since the box is moving to the right, the leftward net force means that the box was slowing down. Again, let's imagine a puck that's sliding along a very smooth surface. If you tap the puck in the direction that it's sliding, the puck will speed up. If you tap the puck opposite to the direction that it's sliding, the puck will slow down. If you give the puck a tap that is perpendicular to the direction that it's sliding, the puck will change its direction of motion. On an ideal, perfectly smooth surface, if you don't touch the puck at all, then it will continue to move in a straight line at constant speed indefinitely. Now, imagine that the robot Wally is moving through outer space while holding the fire extinguisher. If Wally shoots the extinguisher so as to create a force on himself in the direction that he's moving, he will speed up. If Wally shoots the extinguisher so as to create a force on himself opposite to the direction that he's moving, then he will slow down. If Wally shoots the extinguisher so as to create a force on himself in a direction perpendicular to the direction that he's moving, then he will change his direction of motion. And if Wally doesn't shoot the fire extinguisher at all, then he will continue to move in a straight line at constant speed indefinitely. In the video description box, there's a link to the scene that shows how Wally uses the fire extinguisher to speed himself up, to slow himself down, and to change his direction of motion. In video 1, T sub x is trying to speed up the block, and the kinetic friction force is trying to slow down the block. The magnitude of T sub x exceeds the magnitude of the kinetic friction force, so the block will speed up. In video 2, W sub x is trying to speed up the box. The kinetic friction force is trying to slow down the box. The magnitude of W sub x exceeds the magnitude of the kinetic friction force, so the box will speed up. In video 3, the kinetic friction force is trying to slow down the box, and there are no opposing forces, so the box will slow down. So, on each of these 3 problems that we've worked on, the net force determined whether the object would be speeding up or slowing down, in accord with Newton's second law. Now, let's discuss the meaning of the concept of net force. Remember that this expression and this expression stand for the x and y components of the net force. The sigma symbol means add, so these expressions remind us that the net force is the sum of the individual forces. But forces are vectors, so when we add the forces, we must take the directions of the forces into account. For example, in video 3, the normal force is 392 newtons pointing up, while the weight force is 392 newtons pointing down. Adding these 2 forces does not result in a sum with a magnitude of 784 newtons. Instead, since these 2 forces have equal magnitudes but opposite directions, when we add these 2 forces, they cancel each other out. Working with components is helpful because the signs of the components take into account the directions of the forces. For example, in video 3, N sub y equals positive 392 newtons, and W sub y equals negative 392 newtons. So the net force in the y component equals positive 392 newtons plus negative 392 newtons, which equals 0. That confirms that when you add these 2 forces, they cancel each other out. Let's consider another example. In video 1, T sub x has magnitude 10 newtons and points to the right. while the kinetic friction force has magnitude 2.4 newtons and points to the left. Adding these two forces does not result in a sum with a magnitude of 12.4 newtons. Instead, since these two forces have opposite directions, when we add these two forces, the kinetic friction force will partially cancel T sub x. T sub x equals positive 10 newtons, and F sub kx equals negative 2.4 newtons. So the net force in the x component equals positive 10 newtons plus negative 2.4 newtons, which equals positive 7.6 newtons. So we see that the net force in the x component is positive. And we know that the net force in the y component in this video was 0. So the net force points in the positive x direction, which is to the right. So the acceleration also points to the right. To review, the net force is the sum of the individual forces. But forces are vectors, so when we add the forces, we must take the directions of the forces into account. One of the reasons why working with components is helpful is because the signs of the components take into account the directions of the forces. Now let's discuss the difference between mass and weight. The mass of an object can be loosely defined as a measure of the quantity of matter contained in the object. For example, a bowling ball has a greater mass than a marble, because the bowling ball contains a greater quantity of matter. For another example, a bowling ball also has a greater mass than a soccer ball. That's largely because the soccer ball is filled with air, while the bowling ball is solid, so the molecules are more densely packed together in the bowling ball than in the soccer ball. The weight force on an object measures the downward pull on the object due to the Earth's gravity. By the way, this definition and this definition both apply to an object that is on or near the Earth. For example, on the Moon, the weight force would measure the downward pull on the object due to the Moon's gravity. The meaning of this formula is that the greater the quantity of matter contained in the object, the greater the downward pull of the Earth's gravity on the object. For example, a bowling ball contains a greater quantity of matter than a soccer ball. So, a bowling ball feels a greater downward pull from the Earth's gravity. That's why it's more difficult to hold a bowling ball motionless in your hand than to hold a soccer ball. Don't confuse the concept of mass, which represents the quantity of matter, with the concept of weight, which represents the downward pull from the force of the Earth's gravity. If you take a bowling ball from the Earth to the Moon, the ball's mass will stay the same in both locations, because the ball still contains the same quantity of matter on the Moon that it did on the Earth. But the Moon's gravity is weaker than the Earth's gravity, so the ball will feel a weaker downward pull from the Moon's gravity. So the ball will weigh less on the Moon than it weighed on the Earth. That means that it will be easier to hold the bowling ball motionless in your hand on the Moon than it would be on the Earth. The constant little g is smaller on the Moon than it is on the Earth. So this formula confirms that the bowling ball will weigh less on the Moon than on the Earth, even though the ball will have the same mass in both locations. Well, I hope that this example helps you to see that mass really is a different concept than weight. Now let's return to our discussion of the meaning of Newton's second law. This time let's focus on the relationship between mass and acceleration. Here are the Newton's second law equations. If we solve the Newton's second law equations for a sub x and for a sub y, we get this equation and this equation. Since the net force is on the top of this fraction, these formulas tell us that increasing the magnitude of the net force on the object while holding the mass constant will increase the magnitude of the object's acceleration. By the way, I'm referring to magnitudes here in order to avoid the complications that arise when the components are negative. So again, these formulas tell us that increasing the magnitude of the net force will increase the magnitude of the acceleration. Now, what about the mass? Remember, mass measures the quantity of matter that is contained in the object. Since m is on the bottom of the fraction, these versions of Newton's second law show us that increasing the object's mass while holding the net force constant will decrease the magnitude of the object's acceleration. Increasing the denominator of a fraction makes the fraction as a whole smaller. 4 is a bigger number than 2, but 1/4 is a smaller number than 1/2. So again, this version of Newton's second law shows that increasing the object's mass will decrease the magnitude of the object's acceleration. This means that a more massive object is more difficult to accelerate. That is to say, an object that contains more matter will be more difficult to speed up, and more difficult to slow down, and more difficult to change its direction of motion. A more massive object is more difficult to accelerate. Imagine a 1 kilogram puck and a 20 kilogram puck, both sliding along a very smooth surface. Now, it would be very easy to accelerate the 1 kilogram puck. It would be very easy to speed it up, or to slow it down, or to change its direction of motion by giving the 1 kilogram puck a tap in the same direction it's moving, or a tap in the opposite direction it's moving, or a tap perpendicular to the direction that it's moving. But because the 20 kilogram puck is much more massive, it contains a greater quantity of matter, the 20 kilogram puck would be more difficult to accelerate. It would be more difficult to speed it up, or to slow it down, or to change its direction of motion. A tap that would have a big effect on the 1 kilogram puck would have a much smaller effect on the 20 kilogram puck. So we can see now that increasing the mass of an object has two separate effects on the object. Effect number one, a more massive object is more difficult to accelerate. That is, an object that contains a greater quantity of matter is more difficult to speed up, or to slow down, or to change its direction of motion. And, separately, effect number two, a more massive object has a greater weight. That is, an object that contains a greater quantity of matter will feel a greater downward pull from the Earth's gravity. Because of these two separate effects, mass is a difficult and subtle concept. I believe that historically, an imperfect understanding of these two effects of the mass, and a failure to carefully distinguish between mass and weight, was one of the most significant barriers to the development of the science of physics. Remember, the mass determines how difficult the object is to accelerate. Imagine taking the 20 kilogram puck from the Earth to the moon. The puck will weigh less on the moon because it will feel a smaller downward pull from the moon's gravity. So it will be easier to hold the puck motionless in your hand on the moon than it would be to hold the puck motionless in your hand on the Earth. In contrast, the puck will have the same 20 kilogram mass, the same quantity of matter on the moon as on the Earth. So the puck will be equally difficult to accelerate on the moon as on the Earth. So if you imagine the puck sliding along a very smooth surface on either the Earth or the moon, it would be equally difficult to speed it up or to slow it down or to change its direction of motion, either on the Earth or on the moon. Again, I hope that this example helps you to see that mass really is a different concept than weight. Now, I mentioned in a previous video that the biggest mistake that physics students make is mixing up the concepts. For example, students mix up velocity with acceleration, or students mix up mass with weight. To avoid mixing up the concepts, don't use the word it. Don't say it indicates the direction of motion, or it refers to speeding up, slowing down, or changing direction of motion. Instead, say velocity indicates the direction of motion, or acceleration refers to speeding up, slowing down, or changing direction of motion. Don't say it measures the quantity of matter, or it represents the downward pull from the Earth's gravity. Instead, say the mass measures the quantity of matter, or the weight force represents the downward pull from the Earth's gravity. Even when you're simply thinking about the concepts in your own head, try to avoid using the word it. Instead, always label the specific concept that you're thinking about with a name or a symbol. Now, this advice applies to all the concepts that you'll encounter in your entire physics course, not just the concepts we've discussed in this video. Don't mix up x components with y components. Don't mix up coefficient of friction with force of friction. Don't mix up the various forces with each other. Don't mix up individual forces with the net force. Don't mix up position with displacement. The biggest barrier to understanding physics is mixing up the concepts. To avoid making that mistake, don't use the word it. To end this video, I'd like to give a couple of problems for you to work on your own. It turns out that Newton's first law is actually a consequence of Newton's second law. So problem 1 is use Newton's second law to prove Newton's first law. Now let me introduce problem 2. It used to be thought that heavier objects fall faster than lighter objects. And that seems like a natural assumption because a heavier object does feel a stronger downward pull from the Earth's gravity. So it seems natural to expect that a heavier object would fall faster. But it turns out that if both objects are massive enough for the effects of air resistance to be small, a lighter object will fall at approximately the same rate as a heavier object. And in a vacuum, where there's no air resistance, a lighter object will fall at exactly the same rate as a heavier object. You can try this experiment. Try dropping a piece of paper and a textbook you don't like simultaneously from the same height. You will see that the textbook hits the ground much sooner than the piece of paper. But that's because of the effect of air resistance on the paper. So now try crumpling the piece of paper into a tight ball. That will largely eliminate the force of air resistance on the paper. Now, try the experiment of dropping the textbook and the tightly crumpled ball of paper simultaneously from the same height. I think you will see that now both objects hit the ground nearly simultaneously, even though the textbook is still much heavier than the piece of paper. Look in the video description box for a link to a video with an experimental demonstration that in a vacuum, a feather falls at the same rate as a metal cube. Now, have you noticed that we take all of that for granted in projectile motion problems, where we say that all objects fall with the same magnitude of acceleration, little g equals 9.8 meters per second squared, regardless of their weight? So here's problem 2. Use the concepts we've been discussing in this video to provide a verbal explanation for why, when the effects of air resistance are negligible, a heavier object will fall with the same acceleration as a lighter object, even though the heavier object does feel a greater downward pull from the Earth's gravity. And part B, use Newton's second law to prove that in free fall, when the effects of air resistance are negligible, all objects will fall with the same magnitude of acceleration, little g, regardless of their mass. And here's one more problem for you to try. Did you find this video to be helpful? If so, you can support the videos by using the PayPal donate button on my website to make either a one-time donation or a monthly pledge. You can visit my website by clicking the link on the screen or by using the link in the video description box. Thank you.